Okay, good morning. Welcome. So today, lecture on object description. So we had a first series of lectures on segmentation. And as you remember, I will once again show you this drawing. So what we are doing is to try to investigate the complete chain from sensors to decision. This is the typical chain for pattern recognition, image analysis. And so what we have seen so far is really what we have from the pixels to the objects. So this is basically image processing, signal processing, and we have seen the pre-processing, we have seen the segmentation methods, and last time, we have seen the active contours, which is a kind of an advanced method for image segmentation. So now what do we have? We don't anymore have stupid pixels, we have objects in terms of binary shapes in an image. From the original image, we have now object described as a binary object, a binary set of pixels. And so what we are going to do today is to see how to describe them, to go from objects to features. We are not yet at the classification level. This will be for the last course. But we will describe that. And next time, we will see how to classify based only on the features. So no object anymore. And at the end, we will have our decision. So today, this is what we will do. Okay? Clear? Okay. So let's go. The goal is not, again, as usual, not to be exhaustive. I don't want to see all the possible features. There are many. You will experiment some of them in the labs. You will learn more of them in other courses. But today, I want to see some of the foundations as usual. And so what we want is to present the main methods on 2D images, 2D shapes, 2D binary masks, to describe the object present in that image. So from the 2D shapes that we have, which are binary, we want to extract features. Features are the elementary descriptors. They describe the shape of the object. They describe the object. And this is very much application dependent. If you want to recognize a small object versus a large object, the feature that you will use is probably the area of the object. But if you want to recognize a cat and a dog, well, the size might do it. But I mean, if you want to recognize other types of objects, the area is not enough, obviously. So it's very much application dependent. And it can be very simple, like the area, which obviously is a lossy, an elementary description. If I give you the area, you cannot recover the original object itself. But it can also be lossless. It can be the whole object as such. And we will see, for instance, if I use the contour of the object as a feature, as a descriptor, which we will see, well, you can recover the shape of the object because you have it. So there is a large variety of descriptors that you can extract from a binary shape. We will call them features. Okay? So that's basically what we are going to see today. And what I will see is a series of very nice, powerful descriptors that will be helpful for you in a large variety of applications. Not all of them. You will find in the literature many more features that we will not see today, but it gives you already a nice picture of what you can do and a nice set of tools that you can use for so many applications. What we will try to see is what is the quality of a good feature. So basically, we want to use them for classification. So we want them to be informative for the application you want to tackle. So there are a certain number of properties that we want. And that's very important when you think of the features that you want to extract from objects. And if you read them with me, I'll try to explain. Small intra-class variance, large inter-class variance. What does it mean? Well, it basically means that we want to use those features for classification. We want to use them for recognizing, describing, and then in 2 weeks, classifying the objects. So basically, we have classes of objects. I have cats and dogs. Pictures of cats, pictures of objects representing a cat, object representing a dog. And I want to build at the end, at the very end of the course, I want to build a classifier based on the features. So basically, small intra-class variance means that within the class of all the dogs and within the class of all the cats, I want my features to be very much similar to each other. compact. And I want to have a large interclass variance. Between the two classes, I want the features to be in their feature space, very much split apart. So if I extract, for instance, 2 features per object, which is a simple case, I have my 2 binary images, one of a cat, one of a dog, and I extract 2 features. I don't know which ones, but 2 for each of them. Then that means that my feature space is a 2D space. Each object is represented by 2 features, so by a point in a 2D plane. And I will have a point for all my dogs, a point for all my cats, and I really hope that the cloud of points representing typical cats and typical dogs will be compact clouds, while the 2 clouds will be split apart. This will make the job of the classifier simple. This is valid in 2D, in 3D, in n dimensions, of course. And that's important when you choose and you evaluate the quality of your features. You want to have a small number of them. Why? Why do you think you need a small number of them?
To avoid overclassification.
What do you mean by overclassification?
For example, if there are too many criteria, maybe a cat will be described by one type of cat and will not be able to recognize.
Right, okay, so you don't want to be too specific, that's what you mean. Because intuitively, the more features you have, the better the description. That's the intuition. But too many is not good, perhaps because you will not be very general. You will be specific to the class you trained the features on, you choose the features on. That's correct. But there is another important reason. Do you have a feeling why we want to have a low number of features?
Computation power.
Computation power, that's sure, that's always the case. But okay, it can be solved. But I agree, yeah. But there is another one. Have you heard about the curse of dimensionality? Does it sound familiar to you? Curse of dimensionality is not the curve of dimensionality. It's not a curve, huh? It's the curse. And the curse in French, la malédiction. Okay? The fact is that if you want to imagine your feature space, imagine a 2D feature space, you have 10 images of cats, 10 images of dogs. So 10 points on my 2D plane, because I extract 2D features, 10 points for the cats, 10 points for the dog. They are nicely compact. You see them? They kind of fill nicely the space. Now imagine that you only have 10 of those images again, 10 cats, 10 dogs, in 3D. 3 features. Then the number of points that you have looks much smaller in 3D because it fills the space much less. And in 4D, you will only have 10 in a 4D space. And in 100D, you have 10 lost points somewhere in a 10D space. So the quality of the representation very much depends on the number of features. To represent nicely a class, you will need many more points in a high-dimensional feature space. And it is really exponential. If I fill my space, my 2D space, with 10 points, I describe my class with 10 points in my 2D feature space, intuitively, you would need 100 of them in 3D to have the same kind of sampling of your space. And you will need 1 million. 100? No, 1,000? 1,000 in 3D? Well, whatever. It's exponential, right? You need many more. This is the curse of dimensionality. To really capture the essence of a class, it grows exponentially with the number of features. So if you have less, it's good. It doesn't describe the class so well, but you need less points to represent it. And when we'll talk about classification, it means you will need less points to train a system with a given quality. If you want to go with more features, yes, it's good. It will be more powerful in terms of the ability to discriminate two classes. But you need exponentially more points to describe each class. This is the curse of dimensionality. This is very important. This is a fundamental principle in machine learning. Small number of features. Small doesn't mean anything, but as small as you can, but not too small, otherwise you are not discriminant enough. Independence. Independence is a general property of the features that we need in general. For instance, you typically say, I want to be invariant in translation and rotation. Because this is a pointer, but this is a pointer as well. I do it again. This is a pointer, and this is a pointer also. The same object should be described but by features that do not depend whether my pointer is here or my pointer is here, obviously. So I generally, typically, it's not completely stupid to say that the features describing the shape of an object, the shape, should be translation, rotation invariant. Should they be scaling invariant? This is a pointer, and this is a pointer, right? But this is a pointer. If you want to say this is a small pointer and this is a big pointer, of course you don't want to be scale invariant. Or this is a small dog and a big dog, of course you don't want your feature to be scale invariant, if the scale matters. But in this case, at least being translation and rotation invariant is generally a good idea. Okay, clear? Okay, this is what we want to do. Now, I will see a series of descriptors, and I will see them one by one, and there is no obvious link between them. It's just the fact that I want to see them one after the other. Okay? So we will see some of them that I will call external, some of them I will call them internal. The external ones are those that will describe an object based on its contours, very much like the contour extraction, the edge detection methods for segmentation. And some of them use the actual shape as a whole, and they are called internal, very much like the region growing in segmentation. So these are two types. But let's go. Let's go one by one. So I want to describe the shape of an object, and I have the object as a binary image. Let's see the very first one. The very first ones are those based on the contours. I have the contour of my object, obviously describe my shape. I can use the contour itself to recognize an object. Why not? So I can basically use the contour itself. Alors, there is a series of things to say about what a contour is, but we describe it as a set of points that are ordered one after the other in a certain order. So this is the contour, the series of points that represent the boundary of the object. And we will use that. So the very first descriptor that I want to see with you is the contour itself. Can I use the contour itself to describe an object and to see if I can compare it with another one? Because the goal at the end is to compare objects, to say, these are dogs, these are cats, so my new object, is it a dog or is it a cat? So I can extract the contour and look at the contour. And a way to classify is to say, okay, the contour that I see looks very much similar to the contour of the dogs. Then it's a dog. Or looks very much similar to the contours of a cat, so it's a cat. Very much similar, I will translate that into a measure of similarity between contours. Can I measure the similarity between a contour A and a typical contour of my class 1? And can I measure the similarity between my contour and a typical contour of class 2? And depending on whether my contour is more similar to 1 or 2, I will classify in 1 or 2. So basically, we'll try to define what is the similarity between contours, and this will be done by defining what is the distance between two shapes, two contours. So what I will see now is try to see with you the definition of the distance between two contours. I take my contour, and I look at the distance between a typical contour of class A. Distance, the terms small, big distance. Same for class B, and I will classify, obviously, in the class that has the smallest distance. And in this case, the distance to what I would call a typical cat and a typical dog. Simple, huh? So this looks simple, but you see that we can already elaborate a little bit on that. So what is the definition of the distance between two contours? I give you one definition which has some nice properties. I have a set of points. My contour is a set of points, as I said. Huh? So the distance between two sets of points, A and B, I give you the definition, is the mean value over all the points of the distance between each point of A and the closest point in B. So you see my contour A, a typical contour of class 1, we call it B, and we look whether they are similar by calculating for each point of the first one what is the closest point to the other, and doing that for each of the points, and doing the mean. The distance elapsed, the mean value. Obviously, if the two contours perfectly overlap, are exactly the same, the distance will be 0. If they differ from each other, the distance will be a bit more than the 0. Okay? So let's first see that. You might already see that it's not necessarily exactly what I want. But at the end of the day, I can say those two shapes are pretty similar because if I superpose them, the distance between A and B is pretty small. And if one of the shapes would be a dog, the distance would be much bigger. We will elaborate on that, but the basic tool indeed is to calculate the distance between two sets by this definition. Okay? And you can already think what we will do with this distance to really measure a similarity between two things. This is not exactly the same. You will see why in a moment. But okay, let's say the building block will be indeed the distance between two sets. This is not a it's interesting definition, but it's not computationally, it's a little bit heavy. If you want to do that many times, because for each pair of contours that you want to measure the similarity of, you have to take each point of the one and check what is the closest point in the other. So if you do it brute forcefully, you would need m times n. N is the number of points in the first object, n is the number of points in the other. You will have to do n times n operation each time you want to evaluate the distance. Plus, those distances are actually floating numbers, and actually you don't really need that, but if you want to be precise, floating is what you need, and it might take some time, some places in memory. This is a bit historical, though. But I mean, if you really want to do that millions of times per second for some reason like training a network, for instance, having floating is not necessarily the best idea. So two issues there, but a nice definition. And what I want to do now is to go in the details of how to cope with those two limitations to really estimate efficiently the distance. And after that, I will see how to use this distance to estimate the similarity between two objects. Is that clear? Okay, good. So the definition is clear, but there are two issues. Let's tackle the first issue. Imagine this scenario. I have an object, and I want to compare it to a large number of typical shapes. For instance, I want to compare it to all the prototypes of a class. Or I have a lot of classes, and I want to compare it with many objects. Each time, I would have to recalculate a large number of operations. So I want to simplify that. And the first simplification that I propose is, well, okay, you know, my objects that I want to compare them are all different, but my initial object is always the same. So instead of each time finding for each point of the one the closest, or finding for each point of the other the closest of A, I can do something a bit more clever, which is what is called a distance map. Because remember, each time I have to take a point of an object, find the closest point of the other by searching for all the points. So a way to speed up that, and it's just a way to speed up, is to calculate once and forever what is called a distance map of the object that doesn't change, of one of the objects. And a distance map is simply an image which has values at all the points of the image. So values everywhere. It's not a binary image anymore. It's an image. And the value of a pixel in that image is actually the distance to the closest point of the object, of an object. So the distance map of an object A you see it here in white. The distance map of A is an image that is pre-calculated, and it gives you immediately the distance between the point you are looking at and the closest point in the contour. How to build that is the next question, but you see what it is. Because now, if I have this distance map, it becomes very simple to calculate the distance between A and any object B. Imagine, and I didn't say how, we have this distance map. Is it clear? Do you see what it is? So we have this distance map. We calculate it in an efficient way, let's say. And now we want to calculate the distance between A and B. B is another object. So what do I have to do? I take B. B, let's make it simple. B is a circle. And I want to calculate the distance between the circle and my silhouette here. The circle is that, okay? Well, now it's simple. I have the distance map of A, of the silhouette. If I use the definition, I would have to take each point of the circle, and for each point, go through all the points of my silhouette and see which one is the closest. Huh? This is n times n. Now it's simpler. I just take my circle, I put it on the distance map, and I just have to look at each point of the circle, what is the value of the distance map at that point? Because the value of the distance map at that point is already pre-calculated as the distance to the closest point. So I just have to calculate the mean value, or the square root, or it can be the square mean, the mean square value, or the mean, or whatever the distance you want to calculate, but still you calculate the mean value of the values of the distance map on the points of B. The values of the distance map of A on the points of B. And if you want the square distance, you put it square. If you want the root square, you put a square root, whatever. But you use the points of your object B, and you take the value of the distance map of A calculated on the points of B. And then you only have n operations to do. You will say, yes, but it has a cost to calculate the distance map. Yes, but imagine that I have my object, and I want to compare it to 100 possible templates. Then I will calculate only once the distance map of my object, and take each of the templates, put them there, and I will save a lot of time. Even if it costs a little bit to calculate the distance map, I do it only once. Otherwise, I would have to do each time n times n operations. You see? So that's the trick. And the beauty is that there is a fast algorithm to do that, of course. Otherwise, I would not show you. You see the principle of the distance map? Yes? Simple, huh? So now how to calculate it is the next point. So in my two limitations, number of operations was an issue, solved with the distance map. Now how to calculate efficiently and also in terms of memory representation, that's another one. And this is a kind of a superstar algorithm in computer vision, the chamfer distance. What is it? It's actually an algorithm, pretty simple, to calculate the distance map very efficiently. Okay, it calculates an approximation of a distance map, but still it's pretty efficient. The first idea is to say, normally I should say, if I have a point somewhere in my image, this pixel should be at distance 1, and this pixel should be at distance square root of 2, right? That's the Euclid, that would be the floating, the real value of a distance between that point and that point, correct? And the first simplification proposed by the chamfer distance is to say, instead of say 1 and square root of 2, which is 1.41, let's make it integer. It will not change much. Let's make it integer. Instead of 1 and 1.4, we say 3 and 4, which means 3 and 4 are in a ratio which is 1.33333 instead of 1.4. Okay, it's not that bad. So that's the first approximation, to say I will calculate a distance map considering that two neighbors are not in a distance 1 or square root of 2, but 3 and 4. That makes my calculation simpler because I can code that on simple 8 bits, or at least integers. And the second is to propose an algorithm to calculate that distance map. And it's pretty simple because it has two passes, one direct and one inverse pass on the image. You go from top left to bottom right, and you browse the pixels, and you build a distance map. And then you go from there, you go back, and after those two passes, you have your distance map. And I want to show you how it works on the board. Very simple. And it's a principle that we will see quite often, actually. Let's imagine we have contours in an image, and we want to build a distance map of those contours. So we have a contour here, and we have another contour here. This is my image, okay? And I want to build the distance map of this contour. I only see a piece of it here. You don't need to take notes because it is recorded. You can watch the video if you wish. Do what you want. So the idea is to say, okay, obviously, what is the value of the distance map on the contours? What would be the value of the distance map on the contours? 0, okay? The distance between the points on the contour and the contour is 0. So I initialize, obviously, my distance map. Okay, there are pixels, and I don't draw the pixels here, but you can imagine that there are rows like that, and columns and rows of pixels. Huh? Okay, here we are. So, initialization. I initialize the distance map as 0 on the contours. And then I initialize the rest as infinity, a very high number. And then I will say, okay, look, this is my reference for the distance between neighboring points. So obviously, let's take the first point, a point here. I will take another color. The first, the point which is one layer inside my object. Let's say this one here. Obviously, this one is at a distance 3. We say 3, not 1. Huh? 3 of this one, and 3 of this one. So obviously, 3. And I will actually change a little bit my contour, and I will make it like that. Like that, okay? Like a corner. Now, next one. This one. This one, I know something about it. I know that its neighbor was at 3, or its neighbor is at 0. So, the distance map value of this point is either 3 plus 3, 6, or 0 plus 3, 3. What do I choose? Obviously 3, huh? For that reason. Okay, I continue. This is, let's say, I will not do all of them, of course. Huh? So you trust me that those ones will all be 3 because of that. They could be either 3 or 6, either 3 or 9, either 3 or 12, but obviously I choose 3 because of that neighbor, correct? And I continue, tak, 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 and obviously this will be 3 as well. Because of this one, because of this contour. Then 0, then 3, 6, 9, 12. Correct? Now here, what do I have? Obviously I have 0, 3 or 6, so I will choose 3. This one could be 6, 6, or it could also come in diagonal, 6, 6, or 7. Correct? Yes? 6, 6, or 7, it's 6. This one can be 9, 6, or 7, so it's 6 because of that. Check, check, check. And this will therefore remain 6, and it will be 6 here as well, because I'll always look backward to considering the numbers that I have already annotated. And you see that this is actually not true, because the system with the forward pass considered that this is a distance 6 of that point, but didn't see that it's actually a distance 3 from the other contour. But that's life. And then it continues, 0, 3, that will be probably 6, yes, and so on.
On the edge, shouldn't you see the right pixel?
Well, in the forward pass, we just look backward. We look what we already annotated.
So on the kernel, the 0 is the point of our pixel? Or
the 0 is the point where I am, yes.
If you don't use the right part of the matrix?
Not yet. Not yet. Yes, because we just know what is the distance of the contours we have already seen when we move that way. But that's why we will do the other paths, of course. Exactly. And so on, and so on. So we'll basically fill the space like that with growing numbers. And obviously here, somewhere here, we'll have big numbers, which will be basically the distance to the closest point of that part of the picture. Right? So we'll have a kind of a growing value, then another 0 and another growing value. And then you take the opposite. You do the inverse pass. And you start from here. And you will actually correct the errors that you have done because you didn't look forward. And so you will basically correct. So starting here, it will be kind of okay. But arriving here, you will say, okay, I'm not moving that way. So I thought it was a distance 6 of that contour. But actually, I have to correct. I have always to take the minimum. And the minimum is actually a 3 because I'm close to that one. So by doing a forward and a backward pass, you first do the calculation by looking at the contours that you have already seen and how far you are from the contour that you have already seen. And then you correct by doing the opposite. Yes? So this is a very simple two-pass algorithm. And it gives you a very nice distance map. And I'll switch the light on. Not the light. Or do you see correctly like that? I can keep it like that. Okay. So, a simple algorithm. How it is described is exactly what I did with my clay on the board. Eh? Yeah.
And the inverse, do you go from the lower right-hand side to the left-hand side, or can you just take the same mattress and go over the same? You could theoretically take the same path and just go over the same.
If I start again here, no, it will be exactly the same. So it was initialized with infinity, and now you fill it, and you always take the minimum, but you don't look forward. You only look backward on the contours that you have already seen. And suddenly you discover there is a new one. Okay, you made mistakes, so when doing the opposite pass, you will correct that. And that's, with the indices, this is what is written there. Okay? And at the end of the day, you get something which is very similar to an Euclidean distance map, a real distance map. It's not totally Euclidean because this is not really the values of an Euclidean distance. It should be 1 and square root of 2. But it's close to that.
Can you just repeat that part about this, why we got 3 and 4 instead of...
I should repeat why.
Yeah.
It's just to make it simple. Instead of handling values of the pixel and its neighbor being square root of 2 and propagating floating number there, at the time where the chamfer distance was invented, it was interesting to say, rather than propagating ones and square root of 2, we propagate 3 and 4, because the ratio between 3 and 4 is pretty much the same as between 1 and the square root of 2. Pretty much. It's an integer approximation of the same relationship. Now, question, what is the distance map of a single point? I take a point, my object is a single point, here. What is the distance map of that?
Concentric circles?
Yes, it's an image where at each point you have the Euclidean distance between the pixel and my center. And the isocurves, what you mean are concentric circles, you mean that the isocurves, the curves of equal values are circles, obviously. Well, this is what you get if you calculate, indeed, the distance map with the Euclidean distance, which is 1 and square root of 2. But if you calculate it with this approximation, what you actually get is not concentric circles, but that. Which looks kind of almost like concentric circle. What is it? This is the distance map modulo something so that you see it. So when it reaches a certain value, let's say 10, it goes back to 0, so that you see actually the isosurface. But the actual distance map, you don't see it. It's just, what is it? Dark and gray, lighter and lighter and lighter and lighter, and you would not see really the isocurves. By doing a modulo, you see them. But this is why it is called chamfer distance. Chamfer is the English term for French chanfrein, what you have on top of a window. or what you have in the brand of one of those car manufacturers, Citroën. It's true, it's chamfer. And that's why it's called chamfer distance, because you see it there. Okay? That's the history. I should remove that from the video. Okay? So, now, what do we have? We have, okay, we are going into details, but now we have a nice algorithm to build a distance map. Now let's come back to the similarity between two objects, because this is what we want at the end, right? So we want to have an object and say whether it's similar to class A or class B. So we'll calculate the distance with a typical object of class A, the distance to a typical object of class B, and now we have a very nice algorithm to do that. We build a distance map and we calculate the mean distance. Do we have the solution of our problem? Can we say that when the distance is small, the objects are similar or not? Almost, I would say, but why almost?
If you have, let's say, a rectangle, transform the whole image. One is vertical, the other horizontal.
Yeah, but I agree. I agree with you. If you have one rectangle horizontal and one vertical and one rectangle horizontal, they are the same, but the distance will be quite large. What should you do? You have this tool of the distance, but you still have to play with it to convert this distance into a similarity. So what would you do in your example?
Well, you could take a trend from each of the contours and then see the angle between the two. Like, let's say.
And then when you have the angle, what do? You
try to rotate it.
What he's saying is that you should align your objects. You should see your rectangle is vertical, your rectangle is horizontal. You should first look at the geometrical transformation that matches your object. The geometrical transformation that minimizes your distance. That's the way to register, to match them. So that's the beauty of it, and you are absolutely right. If you want to use the distance to measure a similarity, first thing you have to do is to say, I take the two objects I want to compare, and I find the matching by transforming one of them to minimize the distance. And my similarity is the remaining distance. If after minimizing it, I don't have 0, that means that they are not similar to each other. They are not the same to each other. If I still have a little residual distance, this is my measure of similarity. And that's the beauty of it. Why? Because you can say, I have a rectangle like that. I have a rectangle like that. I want to find the translation and rotation that minimizes the distance, and then the residual is my measure of similarity. By doing that, this residual is invariant to rotation and translation, because you basically cancel out the translation and rotation. You want to be invariant in scale. You have a small vertical and a large horizontal rectangle. What do? You want to be invariant to the scale. You want to say those two rectangles are the same up to a rotation, translation, and scale. Well, you just say, I find the rotation, translation, and scaling of that object here such that I minimize the distance to the other. And after minimizing, if the distance is 0, that means that they are the same up to a rotation, translation, and scaling. And if you don't want to be invariant in scaling, you take your big rectangle, you minimize the distance with the small one, you will have a large remaining distance. That means that they are not the same up to a rotation and translation only. So that is what is written there. Thank you very much. You calculate the optimal transformation of one of the objects such that it minimizes the distance. The optimal transformation by the transformation you want to be invariant of. Minimum distance after a transformation that you want to be invariant of. That's the trick. When you have this trick, it's easy. And then the minimum distance at the end is the similarity after this transformation. If you want to compare an object seen like that and an object seen like that with a projective transformation. You see my pointer, you see it straight. Here you see it from the side. The difference, if you take a picture of that and a picture of that, the difference is not a rotation, it's not a translation, it's an affine transformation. It basically stretches one axis. You want to say that, those two pictures correspond to the same object? Yes. Just take the second one and calculate the best rotation, translation, and scaling along one axis, best affine transformation that minimizes the distance between the two contours. When you have done that and found your minimal, the residual distance in this case will be 0, means that the two objects are the same, independently of the projective transformation. This is kind of powerful. And you can do that very efficiently. Now remember, you take the two rectangles again, and you want to minimize the distance. So each time you have to do, obviously if you want to minimize the distance, you have to do it iteratively. So each time you have to calculate the distance between the two. And that's where having a distance map of 1 is interesting, obviously. Because otherwise, right? So you see now, all the blocks should come together now, more or less. What time is it? Okay, good. So we are done for the contours. So now, first way to compare two objects, calculate the distance after geometrical transformation. This is the first similarity measure. This is very powerful. It's a bit heavy. But it's a very principled way to make it invariant to the transformation that you want to be invariant against. So you have the freedom to do it because it's a bit heavy, but you control the invariance that you want.
But how can we find the optimal transformation among infinite transformation with zero?
The transformation is the one that minimizes the distance.
Yeah, but I mean computationally it's...
It's a minimization problem. Then you have your distance map, you have your object, so you calculate the distance between your object, and you do, for instance, a gradient descent. So you estimate the gradient of the distance by calculating the value of the distance if you move it a little bit, and you go down the gradient. It's a minimization problem. You have a function, you want to minimize it now. So you do what you want to minimize it, but you go to your courses on numerical calculus, how do you call it, calcul numérique, and you basically have the minimization of a function. So you have parameters, which is the position and the rotation of your object, and you want to find in that parameters what is the value of the parameters that minimizes a function, the function being the distance. So you have a classical minimization problem. Okay? So you have to iterate, yes. But now if you have this tool, you can say this image is a cat or a dog because you can calculate the similarity between a prototypic image of a cat and a dog. Okay? And then your feature is just the distance. It's a 1D feature, which is the similarity. I want to see another one, and then I will do a break. As usual, I would propose you to do a little bit more now, have a break, do a little bit more, and then stop, as we do normally, just one break. Okay? So I continue a little bit if you are still alive. Okay, clear questions on that? Second descriptor, and also another one. So stop, I finish with the contour. Yes, please.
What do you take as an end criterion for
the value that you get for the distance when you have found the optimal transformation.
So you compare the old and the new result if it doesn't change anymore, because if
Correct.
If you just find the optimal rotation, that doesn't mean that the distance is below a certain threshold.
Well, no. You find the optimal rotation translation. If you want to be invariant in rotation translation, you take your two objects, you rotate and translate one of them until you find the best one by minimizing, as I said. When you have done that, you have a remaining distance between the two. And this value is your measure of similarity. This is the one.
Okay.
If it's 0, you have the same object. If it's small, they are pretty much similar. If they are smaller here, then my object belongs to the last class. Yeah. Okay. So it's a 1D feature.
But the number of transformation is kind of huge.
Yes, it is. That's why I need a distance map.
Oh, okay. But I mean,
Still.
When you say the optimal transformation, you have to search among.
Correct. That's also what your colleague said. It's large, but it's a minimization problem. You have to find the minimum of the function. So indeed, it can be 100 to 1,000 iterations until you reach that. So that's why I said it's a bit heavy as a method, but you control exactly what you do because you know against which transformation you want to be invariant. Okay? Now let's see another type of descriptor, which also is kind of famous in the literature. And it's called the Freeman Code. And I hope you will like it because I hope you will learn something more than a shape descriptor here. You will see why. The idea was simple. Again, it's based on the contours. But the idea is to code the contour, to represent the contour as a series of characters. And the idea of the Freeman Code is to say, if I am at a certain point on the contour, I will code the position of the next one on the contour. So if I'm here and let's say I'm turning counterclockwise, the next point is here. Let's give a code for this direction. Let's say this direction is 1. You can do 4 or 8, but I do 8. 1. So basically starting from here, where do I start? I don't know, but let's say starting from here, I will represent my contour as saying next point is in direction 1. So it's 1. Oh, I'm lucky. Then next point is direction 2. Obviously I started from the right way. No. No. Where is my starting point? Here. Okay? 1, 2, 0, 1, 0, 0. Here I am. 1, 2, 2, 4, and so on. And at the end of the day, at the end of the procedure, when you have done all the contour, you have a string of characters coded from 0 to 7. So first thing you can do with that, this is a very compact representation of an object. Because if each of them, you decide to code them on how many bits?
3.
3, thanks. With 3 bits, you code 8 values, right? Hopefully. So with 3 bits and those many points, you basically get a coding of your object with 60 bits. So first, it's a compact representation of an object. This is the first thing you can remember. If you want to have a very compact storing of an object, independently of where it is in the space, because you don't say where the first point is, you basically represent as a Freeman code with 3 bits, and you have a very compact. And you can reproduce, when you have that, you can reproduce your object. So you code it losslessly, without losses. But you can also use that to compare two objects, and that's the beauty of it, because now you have a string of characters, very much like words. And when you have, in your preferred word editor, when you have 2 characters, you can compare them for doing spell checking, for instance. And so there is a large literature on how to compare to say whether 2 chains of character are similar to each other or not. And this is really what Freeman has proposed. And this is the history of it. We are now moving away from comparing objects. We have represented our object as a chain of characters. Okay, we have only 8 characters. We don't have the alphabet of the 27 letters. But we have only 8 letters. That's life. They're numbers. And we have chains of characters. And we want to say whether the chain of character of my object here is more similar to the typical chain of character of my cats or the typical chain of characters of my dogs. That's what I want to do. So again, I will find a way to measure what is the similarity between 2 chains of characters. And there is literature on that because this is very much what you do in spell checking. You type a word and you do a typo. What the system does for you in real time is to look in a dictionary what is the closest chain of character, the closest to what you typed. And it will suggest the correction by looking at the characters that you have typed, looking at the characters, the chains, the words that he has in his dictionary, and proposing you the closest one, or the closest ones. Closest in which sense? But typically, 2 chains of characters are close to each other if you can convert one to the other in a small number of operations. You did a typo. You reverted 2 characters. Or you did a typo, you put a Y instead of an I. or a Z in terms of, instead of a T or S, whatever. Or O and P on the keyboard. So small number of operations would convert one chain to another. Then we will say they are very close to each other. If you have to do a lot of operations, they are pretty much, it's very likely that they are different words. Okay? And that's the principle. So basically, my notion of distance is the notion of addition distance. I said we will use your preferred word editor. Why is it called an editor? Because you basically edit the characters. You type and you modify the characters. And the distance between two chains is called addition distance because this is the number of addition operations that you have to do to convert one chain to the other. Yeah? And obviously my similarity will be calculated by the minimum number of operations I have to do to convert chain A to chain B. Why the minimum? But obviously, to convert chain A to chain B, I could remove all the characters, insert them again, and change. That would be a valid transformation, but it's not very much, it doesn't correspond to the similarity of the two chains. Or I could take a chain, add 1000A, remove 1001, remove add 1, and do the change. That's valid, but it's not the correct measure of similarity. So obviously what I need is the minimum number of operations. And this term minimum, I really want you to say it when I will ask you to say it, if you see what I mean. Generally, yeah. Suddenly people look to me. I want you to say minimum when I will ask you to say what is the editing distance, addition distance. Okay? Clear? You get the message? So now let's see. I have a chain. Okay, in the Freeman codes of an object is 0, 1, 2, 3, 4, 5, 6, 7. In my examples, they are characters, real characters, A, B, C, and so on. But it's the same, huh? It's just another example. So I generalize what is the similarity between two chains. You can do that to measure the similarity between two objects represented by the Freeman code, obviously. Yes? You follow me there? Yes, obviously. So now, how can we calculate the similarity between that and that? Well, what are the typical operations that I can do? In this context, we consider, for the simplification, 3 types of operations. I can add a character, I can remove a character, or I can substitute a character to another. One single character, I can change it. Okay? There are three elementary operations only. So to go from that, A, B, A, B, A, to A, B, B, A, I can do a lot of possible operations. I can do the most obvious, remove A. My distance of addition, my addition distance would be 1. But I can also say I convert A into B, and then I remove B. That would be 2. Or I can say I add 1000A, and I remove 1001A. I'm stupid, but I can do that. Then it would be 2001 operations, so the distance would be 2001. Obviously, the right answer is the minimum of all of them. So the right answer is obviously 1. I can replace A by a B and then suppress the B, or I can suppress the B, and that's it. So that's the beauty. So the distance of addition between two chains, X and Y, is the minimum number of operations that are necessary. And so if I take two contours, that and the typical cat, and that and the typical dog, and I calculate the distance of addition between the Freeman code of that and the Freeman code of a cat, that and of a dog, and I calculate the distance of addition, I will take the decision to put my object in the one that has the smallest. And this also tells you how we do spell checking. Now, is there a nice algorithm to calculate that? Yes, luckily enough, there is a nice algorithm to calculate the distance between two chains. And that's what I want to do, and then I will do the first break. Okay? So, again, I want to do this because it's a compact representation of a shape, And there is a way to calculate the similarity between two chains of characters because of the literature that exists on spell checking. Right? So now, let's go to the algorithm that will calculate that. So Freeman Code is the representation. Addition distance, I will wait for the picture to come back. Voila, hello, welcome. No, not to you, to the camera. I represent my object as a Freeman Code. I define my similarity as the addition distance that I will use to classify. Now I need an algorithm to calculate effectively the addition distance. Okay? So let's do it. This algorithm has a nice name. You remember it or not, doesn't matter. But the idea is pretty nice, and it has quite a lot of similarities with that one. You will see. The idea is to say, if I have two chains of character, and I will let you read that afterwards, but I take an example. I have a chain of character here, A, B, C, B, and another one, A, B, C, B, C, C. These are the two chains. The idea of the Fisher-Wagner algorithm is to say the number of operations from a very small chain to a very small chain, to convert a very small chain to a very small chain, is simple to calculate, simpler than the number of operations to a bigger chain. And if I have the number of operations to convert a small chain to a small chain, it's pretty easy to calculate the number of operations I have to do between that small chain and one additional character, and the other small chain and one additional character. If we do it progressively, from small to medium to the full chains, then that will be easy. That's the story. Let's see how. We put that in a diagram like that. Here is my first chain, here is my second chain, and I want to calculate the minimum number of operations to convert that one to that one, or that one to that one. And I will fill this table progressively. The idea is to say, you read it like that. This is the empty chain. This is the chain with one character. This is the chain with two characters. This is three, and this is the full. Again, this is the empty, here, this is the empty chain, 1, 2, 3, and so on. And we will do it progressively. What I will put in the box here is how many operations I need to convert what I read here to what I read here. What is the number of characters, the operations that I need to convert an empty chain to an empty chain? Okay? Now I read it like that. What is the number of operations that I need to convert an empty chain to a single character A? One insertion. 1. Okay, I will speed up. 2, 3, 4, 5, 6, 7. Correct? What is the number of characters that I need to convert an A to an empty chain? 1. Remove it. An AB to an empty chain, 2. So this line and these lines, are trivial. And you read them, how many operations I need to convert what I see here to what I see here. So now I have something, and I will continue. Now look. What is the number of operations, the minimum number of operations, to fill this box, to go from A to A? There are three ways. Either you say, it's pretty much the same as going from empty to A, the same number of operations to go from empty to A, plus one suppression. So to go from A to A, I can go from A to empty, and then I read what I have there. Which is true, huh? Or you can say it's very much the same as going from A to empty, and then add an A. So you basically look at what you need to go from A to empty, it's 1, And then you add an A, and you would put 2 there. Or you say, it's pretty much the same as looking at the 2 chains that have 1 character less, empty and empty. And to go from empty and empty, you need 0. And then you still have to see whether you need an additional operations for the last character. If they are the same, you don't need anything more. So the number of operations to go from A to A is very much the same as to go from empty to empty, and you don't have to add anything because the extra characters are the same, so you don't have any substitutions to do. And so you have 3 choices, 2, 2, or 1. Oh, 2, 2, or 0, sorry. Which one? Thanks. 0. Because of that. Because it's the same cost as going from empty to empty, and the remaining character, the last character, is the same, so I don't have any additional operation to do. And you keep going like that. And I will not do the whole table, but let's do it once more. I want to fill that one. How many operations do I need to go from A to AA? Well, 2 choices. Either I go from A to empty and then I have 2 other operations, or I go from A to A and I have 1 more operation, or I go from empty A to AA. So empty A, I know the cost, it's 0. Empty A, I know the cost is 1, here. And I look at the remaining character, and it's an A, and it's an A, so it doesn't cost anything more. So at the end, you look at the 3 possibilities. I think I did something wrong in my last explanation, but you see the story. And it's a 1, because of that, probably, or that. So it's the same cost as going from empty to A and adding another A. You know, it's correct. It's the same cost as going from empty to A, and there is no additional cost because the additional character is the same. Now I will just do 1 more, which is probably this one. And then I will stop. This one is AB to AA. So 3 ways again. Either to go from AB to AA, you say, I go from AB to A. And where am I? Where am I? AB to A, I have it here, because that's, no, sorry. No, sorry, yes. AB to AA, I go from AB to A, 1 operation, and then it's the cost of going from A to AA. So it's that way. So it would be a 2 if I take it here. Or we can do the same for this link, or we can say from AB to AA is the same as from A to A, which is that. And then there is also the last character of each string, but here they are not the same. So I have 1 additional operation, which is to convert the B into an A. So it's 0 because of that, plus 1 because of the conversion. And you keep doing that. 3 possibilities for each. And at the end, you read the minimum number of operations here. And so this is basically what is written in my algorithm here. For each box, you look at the previous one on the left, and you add 1. On the right, upwards, and you add 1. Or in diagonal, and you add 0 or 1, whether you have to still do a substitution of the last character or not. And you do that, and you get the addition distance. And that's basically it. Fisher-Wagner is a nice algorithm to compare 2 strings of characters. If you want to build your own spell checker on your own dictionary of your preferred language that you have invented, now you have a way to do a spell checker, to find the closest words in a dictionary to the word that you are typing. But you also have a way to calculate the similarity between 2 objects, because you calculate the Fisher-Wagner, the addition distance with the Fisher-Wagner algorithm between the 2 Freeman codes of your object. Correct? Questions? What are we going to do next? We are going to go faster. That's the good news. Because I will have very quickly simple things, and I want to spend a little bit more time in the Fourier descriptors, and then I will be mostly done with the content. The rest is pretty fast, and I will see it or not depending on the time. It's pretty simple. You can read the slides as well. But I will spend a little bit more time on the Fourier descriptors just after the break. Okay? So let's do a 15-minute break. Okay, welcome back. So, already two very important features. The contour with its distance, or the distance between two Freeman codes. Now I will go fast to a few more and then spend a bit more time again to a very famous and very nice one that you will most probably use in the lab next week. So let's do it first. If this is okay, voila. No, okay, this one is dead. Yeah, it's probably dead. Doesn't matter. Yeah. Or not. Yeah. If you have a contour, you can also want to simplify it and describe it with fewer points. This is called polygonalization. Polygonalization, yes, something like that, to create a polygon. And I will go very quickly. It's simple. You have your contours described with a very fine resolution, and you want to describe it with fewer points. That could be enough for your application, and then you do what you want after. And doing a polygon from a complicated curve is an iterative operation. I just want to show you that once, and maybe you will use it, maybe you will never use it, but it is pretty simple. So if you have a line like that, and you want to make it a polygon, or a polyline in this case, because it's not closed, it's just iterative. You take 2 points, the two points with the biggest distance, for instance, or if it's a line, the two extremal points, and you draw a line. This is your first approximation of your curve. And when you have that, you look at the point that has the highest distance to that line. And you know how to calculate the distance to a line now. Huh? This is this one. And so your new polygon, or polyline, is this. Then the next point is this one. And very quickly, you come to a very nice approximation of your curve with fewer points, which might be useful for representing in a more compact fashion. Okay? I will not go more in the details. This is just a trick that you can have in your mind or in your toolbox, if you wish. Yes, one important one. You remember mathematical morphology? You loved mathematical morphology? Yes, thanks. One more point. You will use it here to represent an object. Remember, a contour is a nice, complete representation of an object. But this one is nice as well, and you will see it has additional properties, but it's pretty similar. I have an object here. You see it? A drop. It's an example. I want to represent it not by its contour, but by its medial line, medial axis. The axis that goes in the middle. And somehow it's pretty much the same. Because if you give me the contour, I give you the shape. But if you give me the main axis, and if you give me the size of the object around the main axis, I can also reconstruct. So kind of the same. Not exactly, but you will see. And now, how are we going to build this skeleton, this medial axis? There is a vast literature on medial axes as a representation of objects for very good reasons that I will just describe a little bit. But let's see what is a skeleton. We take a shape, binary. We will do binary morphology on it to build this line. And the operations are these ones. The skeleton of my shape, follow me because it's not difficult, but you have to be with me. The skeleton of that shape is the union of small pieces of skeleton. There will be a series of small contributions to the skeleton that I will calculate one after the other. Each contribution is calculated by this expression. And I will read it with you. So the skeleton at the end will be the union of those small contributions. And we will start from the contribution number 0. And then we'll have the contribution number 1, number 2, number 3, and so on. contribution number 0 is the result of this operation with r equal to 0. So it's the result of the object eroded by nothing, r being 0, minus the object eroded by nothing, opened by b. What is b? As usual, b is a small structuring element. I take something very small, a very small ball, with the minimum radius I can. On a digital image, let's say a 3 by 3 cross or a 3 by 3 square, but in continuous terms, it's a very small ball. Circle. So, contribution number 0 is the difference between x and x opened by a very small circle. And now you have to remember what an opening is. What is the result of the opening of x by b? Who can tell me what is the result of the opening of this object by a little ball?
It's almost the contour.
Almost that? No, I'm just asking that. Huh? The opening, not the difference yet.
It's the object.
Almost, but my ball is not a single point. It's a bit more than a single point.
But if you open, you do erosion and then dilation, so at the end you come back to what?
Except something, because the erosion removes something that you will not get back. I remember, an opening is not a null operation. It removes something. What does it remove? The sharp parts, not the edges, but it removes the parts of the image that are smaller than my structuring element. What is the part that is smaller here? Do you see a part where my circle would not fit? Only the tip. My ball will not fit in the tip. It will fit everywhere else, but it will not fit in the tip. If my ball is very small, it will not fit in the very tip. If my ball is a little bit bigger, it will not fit in the tip. So, the opening of x by b is the same except the tip. What is the difference between x and that? The tip. So, contribution number 0, and let's consider that my ball is very small. Huh? Contribution number 0 is this point. I put it on a line, and this is the contribution. Well, it's at that level. In this case, it's obvious that my skeleton is a line. So this is it. It is there, means there, with a value of r equals 0. Now, what will be contribution number 1? What I will do is that I will take my object. I will erode it by 1 time b. And then I will do the same and open it by b. What is my object eroded by 1 time b? It's the whole thing a little bit shrinked. With or without a tip? With. Who said with? Who said without? Sorry, you're wrong. After erosion, you still get a tip. Not the same one, but you get a tip. Right? You agree now or not? I have this shape, I erode it, I have this one. It's an erosion that I'm talking about now. Huh?
But if I just erode?
Ah, that's another story. Wait. But if I have this, and I erode it, I have this. Sure. And there is a tip. Sharp tip. So, I know what this is. This is the same object, a little bit smaller. And I have to do the difference between that and the same opens by b. What will be the result of the opening of that by b? The new tip. The new tip. Still very small, smaller than my structuring element. But here now. So, contribution number 1 is actually this point, somewhere there. And then I will keep going. I will not do it again, okay? I eroded twice, so it will be now this one. I said I would not do it, right? With a tip, the tip being inside, but with a tip. And after opening, it will be that tip, which will be there. And so when I built my skeleton, I build it point by point, or iteration by iterations. There might be many points appearing by this operation. Huh? But I'm building iteration after iterations, and each time I record what I get after this operation, and these are my components of my skeleton. And each time I keep the location of the points, but I also keep in memory the value of R, the iterations at which it appeared. Why? Why is it a good idea to keep that? You don't need it. You see, this is a nice representation of the object, no? Why do you want to keep the knowledge that the value of R here was 20, while here it was 1? Yes, because if you keep that value in mind, you can reverse it, and it's actually written there. If you keep your skeleton, and you redilate correctly each point of the skeleton, correctly means with the right size of the ball, you will get back your object without losses. So this is the skeleton of my drop. This is also the skeleton of a rectangle, more or less. Let's say more or less. But the values of R would not be the same. So if you want to compare two objects, you can calculate the distance between the skeleton of object A and the skeleton of object B, but you have to consider that for calculating the distance, you also have to calculate the value of the skeleton, not only the location of the points. So it's a bit more tricky, but it allows you to calculate something interesting, which is what information does it give? What does it tell me if I know that the value of the skeleton here is large, 20? What does it tell me about the object?
It tells you the location of the greatest mass.
Yeah. It tells me that the object is big at that point. So now, if you want to compare two objects, like those ones, here is the skeleton of that object, color-coded by the value of R. Big R's, medium R's, small R's. And this reconstruction formula allows me, for instance, to say, okay, if I ignore the values of the skeleton that have small values of R, if I ignore them, and I compare objects based on the remaining parts of the skeleton, it's very much like comparing that with another object. So instead of filtering out the parts that might not be very relevant for your comparison, you can just say, I'll calculate distance between the contours, ignoring the small values of R. You just threshold the values of R. You ignore the points that have a lower value. You don't have to reconstruct the object. You just know that by ignoring some parts of the skeleton that have low value, you ignore what is small, and when you compare two objects, they will match nicely that one with the low resolution, it's not resolution, but the scale of the object corresponding to the values that you kept. And you can say those two objects are similar or not. If you only consider the large parts of those two objects, they are exactly similar, exactly the same. If you consider all of them, they are not. Yes, that's true. And you can have a scale representation of your object. That's the beauty of it. Okay? That's all I said about the skeleton. Last main contribution for today. I will not be very long anymore. What time is it? That's okay. We still have like 30, 40 minutes. So, last part, and it's important. Not really last, but last main contribution of today. Fourier, haha, welcome back, Fourier. Fourier, French mathematician, you know him, huh? I'm not French, so it's okay. French mathematician, invented the Fourier transform. I hope you know it. Good news, we will do Fourier transforms of objects. And that's the beauty of it. What is a Fourier transform? It's a frequency representation. A signal can be represented by its low frequencies plus medium plus high frequencies. And this is nice because if you only care about the shape, the general shape of your signal, you look at the low frequencies. If you want to remove the high frequency noise, you cut the noise. Remember my Wiener filter. And we'll do the same here. We will have a Fourier representation of an object. What is the low frequency? And what are the high frequencies of my shape? It's exactly what we will do. And this is very nice. And calculating it is very simple. The only difficult point is that you have to take your contour and build a signal. Because Fourier was a signal processing guy, not an image processing guy. So we would go back to signals. And the idea is to say, I take my contour, and each point of the contour, I create a complex number with the x and y coordinates being the real and imaginary part of a complex number. And then I do that for each point of the contour, building a series of complex numbers. Series of complex numbers is a series of numbers. It's a signal. Complex, whatever. Who cares anyway? Fourier is complex also. Not so complex, but anyway. The only trick here is that you have to take the points one after the other, a point, and the next one on the contour, and the next one on the contour, and the next one on the contour. You cannot do the raster scan. You cannot take point 1, point 2, point 3, point 4, point 5, point 6, point 7, point 8. No, you have to take 1, 2, 3, 4, 5, 6, 7, 8 to build a signal that represents your contour. Very much like the Freeman Code. You cannot do that and that and that. You have really to follow the contour. That's the only difficult part when you will have, and you will have, to code a Fourier descriptor. But when you have done that, you start from any point, and you look, where is the next one? 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 And you build this UK for k going from 0 to what you want. Each of them being a complex number. And that's it. After that, you do what? A Fourier transform. And you know what is a Fourier transform, because if you were at EPFL, you learned that with me. If not, too bad for you. Oh, this is recorded, I should not say that. The other professors of signal processing at EPFL are very good as well. Hello, Mr. President. This is a Fourier transform of a signal. And Fourier transform anyway gives complex numbers. So it applies very well to complex numbers. There's no issue there, no issue. Generally, we don't do that because the speech is not a complex number, a complex signal. But here we have a complex signal, so what? And so we have that. And we get a series. If I have 100 points in my contour, I get 100 Fourier coefficients, complex Fourier coefficients. And these are my Fourier descriptors of my shape. And you have the inverse Fourier transform. So if I give you the Fourier descriptors, you get back the signal. And you can do filtering. How do you filter an object now?
Get rid of coefficients.
Yeah, you calculate the Fourier transform and you reconstruct only with the few first coefficients, as few as you want. You take your object, you reconstruct it with all the Fourier, so you calculate the contour, UK, you calculate the FL, the Fourier coefficients, and you reconstruct it with all the Fourier coefficients, you get it back. Or you say, I reconstruct it only with 10 Fourier out of, I don't know how many I have here, maybe 50. You take only the 10 first in amplitude and phase, or in the real and imaginary part. And you just do the reconstruction of that part of the signal, and you get a low frequency version of your signal. Of course, the two endpoints do not match anymore because on the way you lost some information, but that's okay. But you have a low frequency representation of your object. Now, what you have to do? You have to recognize that in the low frequencies, you probably capture quite a lot of information already. And this is so nice that in many applications, those that we will see in the lab, only using the two first coefficients, only two, will already give you enough information to discriminate something versus something. You will see what. So you can go as low as 2, 3, 4 dimensional space, 2, 3, 4 features only, and still have a very powerful representation of your objects. Look, I'll skip it for the moment, I'll come back. What does it mean? Let's imagine you want to do character recognition. That 1, 2, 3, for instance. And you have a training set of many 1s drawn by hand, many 2s drawn by hand, and many 3s drawn by hand. For each of those examples, you calculate the contour UK, you calculate the Fourier transform, and you keep the two first Fourier. Let's say the amplitude of the two first Fourier coefficients. 2 features only per image, per character. So each point in this 2D space, which is the amplitude of the first coefficient and the amplitude of the second coefficient, each point is actually one of my images. Yes or not? And what you see is that with only those 2 coefficients, all those that were actually written as 1 nicely cluster here. All the 2 nicely clustered, I don't know where, here, and the 3 here. And so, we have what we said at the very beginning. We have a series of descriptors where we have a small intra-class variance and a large interclass variance with few features too, which is good for the curse of dimensionality. So this is very powerful. Now you give that to a machine learning system and it will be very happy. Yeah? That's what we will see next time, of course. Now, this is Fourier. Fourier, very nice, very compact, and very understandable feature. You know that you are coding the low frequencies of your object in the intuitive sense of the term. Now, the better, even better, you can have invariance. And I will go quickly because this is basic signal processing. So I will name the properties. The demonstration is in the slide, but this is kindergarten class signal processing. Yeah? You can be invariant to translation. What does the translation do? Quickly, you take an object, Fourier descriptors, Fourier transform, you change its location, Fourier transform. What will be the relationship between the two? Don't look at the board.
They're the same, right?
Almost. Except? No. Location. First coefficient. You're an electrical engineer?
Yeah.
Yeah. You're an electrical engineer? Yes? Oh, so you should know it. This is the DC component, guys, for the electrical engineers. The DC. You change the location. That means that you basically change the initial value, the 0 frequency. But all the rest remains the same. That's why you said it will not change. You said it will not change. It will indeed not change, except the location, which is coded in the 0 coefficient. So you have to ignore the 0 coefficient. That's why in my drawing it was written A1 and A2, not A0 and A1. Ignore the first one. Translation only affects the 0 coefficient. Now somebody said phase. It was not that wrong, but what was the right question for which the answer was the phase? I take an object in the complex plane. I'm in the complex plane. I code the x in the real axis and the y in the imaginary axis. So doing a rotation in the complex plane, what does it do on the complex numbers? Change the phase. So basically, if I do a rotation, I change the phase. A rotation of my object by an angle theta, my signal will just be complemented by an additional phase to all the coefficients. What does it do on the Fourier transform? The calculation is there. It affects the Fourier coefficients with the same dephasing. What do you have to do if you want to be invariant in rotation? ignore the phase. Just take the amplitude. That's why I had A1 and A2 in my drawing. Only the amplitude. Where do you start? Well, you start from a point. Oh, scaling. No, scaling. Scaling. If I scale from the middle, if I scale my object by a factor A, I multiply all the coordinates by a factor A, my Fourier transform will be multiplied by a factor A. Fourier transform is linear. How to be invariant to scale? It's written there. Don't consider the Fourier descriptors. Consider the ratio between two Fourier descriptors. Consider the ratio between A2 and A1 and A3 and A1. Scale by one of them. If you scale by one of them, you basically remove the scaling factor. So take A1 as a reference, scale all the other by that one, and you have Fourier coefficients. Do that for the amplitude, and you have coefficients that are invariant in rotation, translation, and scale. And you still have some comment here about the choice of the first point, which basically only affects the face as well. And I will not read it, it's simple. At the end of the day, what I have is a very compact representation of my objects as a very limited number of features, which are the amplitudes, if you want to be invariant in scale, the normalized amplitudes of the Fourier transform of the object. And that's beautiful. How many? As few as you can. In this case, to recognize 1, 2, and 3, it seems that 2 is enough. Because it seems that we can draw a nice boundary here and a nice boundary somewhere here. But in more complex cases, it might not be the case, and you might want to add a third dimension to better discriminate your three classes. So 2 is just an example, of course. The beauty of 2 is that you can draw it on the board. 3 would be a little bit more difficult. But it's very usual to have 100 features in complex situations. In the famous machine learning, deep learning technique, where we think there is no feature, there are features in deep learning. The first layer extracts features. They extract millions of features. But they have millions of data to train them. But they extract features, and then they classify them. They try to build a space in which the classes are nicely separated such that the classification layer of a deep network will have an easy job. Don't think that a deep network, if you know what it is a black box which does you don't know what. No, it does feature extraction and classification, but it learns the features and it learns the classifier. But it does that. And it still wants to have not too many features, millions only. No, but that's true. In your lab, you will not deal with millions of features. You will deal with 2. What you will have to do in the lab next week is basically to do recognition of zeros and ones by what you want, but I would like you to test at least the Fourier descriptors. Not recognition, but at least displaying that for the data set that I will give you, showing that indeed, with 2 features only, you choose which ones, but I want at least to see the two Fourier descriptors, you indeed can build classes that are nicely separated. And then I will add you to add the points corresponding to 2 and 3s, and you will see that actually they start to mix up, hopefully. That's what I want to show, for some features. And so this means that probably you want to go to higher dimensional features, and I will not ask you to do it, but just to recognize that you have to do it. That's what you will have to do. You will have the freedom to choose the features that you want as long as you choose 2 of them. And at least I want to see one plot with Fourier descriptors. Do you want to try the invariance in translation and rotation? Please do it. Generate more images by rotating and scaling the data that I will give you and show whether they fit at the same place or not, depending on whether you have chosen features that are scale invariant or not, or rotation invariant or not. So please use your imagination. That's for next week. It was requested last time to have the details of the lab early in advance. It will be online. It is actually online, but I will release it today. Or Monday morning maybe, but today probably. So you can already start the lab this week. Well, next week. before the session. So you can come to the session with good questions. That was the request. Quickly now, what time? That's okay. Actually, I have a train to catch, so that's why I'm a bit in a hurry. More features. Let's go quickly to very basic features. I want to distinguish a big cat and a small cat, or a big dog and a small dog. Obviously, I want to calculate the area of my object. This is trivial. Calculate the number of points. Yeah? The area is the number of points times the area of the point. Yeah? Cool. We are on a discrete grid. So this is true, but actually if you take a circle sampled on a discrete grid, you calculate the true value of the area of a circle by the actual analytical formula. I will not remind you the formula. And then you calculate the number of pixels of the discrete version, and you see that it's not that bad, even for small. These are small objects. Huh? Well, the error is not that small, so it's okay. You will say, why do I take 5 minutes to tell you what an area is? You'll see. There is another way to calculate the area, which is this one. For this object, I could also say the area is actually the number of points inside plus 50% of the number of points on the boundary. Why not? This is what is written there. The size of the pixel, number of points inside, and 50% of the number of the boundaries. And there is a -1 here just to cope to the fact that this is actually not 50%, but 25 here, and even less there. This is another definition. Who cares? Yes, we do. You will see. So, two definitions for the area. 3 definitions for the perimeter. I will not describe them. Read them. Why do I give you several of them? It looks stupid. There is one reason, only one. If you want to use the perimeter of the area as a feature, use any of those definitions, it will work. But if you want to calculate something which is called the compacity of a shape. The compacity of a shape is the square of the perimeter divided by the area. A shape can be very compact or not. Very long perimeter as compared to the area, or a circle which is the most compact object. The object that has the smallest perimeter divided by the area. Squared perimeter divided by area. The smallest compactness. Compacity. This is the definition. And it cannot be smaller than the compacity of a circle, which is 4 pi. And just what I want to show you here is that you have to be a little bit careful when you calculate the compacity of digital objects. Because depending on the definition that you take for the area and for the perimeter, I will let you read that, this is simple. But you might come up with values for the compacity of an object which is actually greater. Which is actually, smaller. Where is it? It cannot be smaller than 4 pi normally. But with some definition, it can actually be. 4 pi is that. Huh? So with some definition, it can actually be. Because of rounding errors. So just be careful when you do that. That's just what I wanted to say. I will not spend more time on that. This is trivial. But just this feature can be a very nice one when you have to recognize shapes. Some shapes are very compact. Some shapes are not compact. So calculating that might be sometimes a very good idea. Okay, the rest is simple. I will let you read this about what is the rectangularity. I will let you read that. I will not spend time here on that. What is the elongation? You have to calculate axes, and I will just spend a bit more time on axes, and then I will be done. Again, just checking how much time I have. Yes, it's okay. I will come back to that, but I let you read that. Projections. This is something that is very much used in optical character recognition. You take a shape, and you basically integrate over the lines and columns to see how many pixels you have in your object at every height and every width of your object. And you say, my object is described by the fact that it has 2 peaks horizontally and 1 peak vertically. Therefore, it's an H. It's an H. This is the typical rule that has been used for many, many years for optical character recognition. I will not spend time on that. This is trivial, but you have it in your toolbox now, because I just show you. Moments. Okay, you have a shape, and you love statistics, right? You love statistics, huh? You all love statistics. So, obviously, you want, very intuitively, to calculate the statistical moments of this function. Statistical moments have the definitions that you love. You remember the statistical definition of the mean and the variance and the first-order moments and second-order moments. This is of a bivariable, 2D variable. The variable being my object, 0 or 1. And so you can calculate the mean and the first-order and the second-order moments and consider that they describe your object. And it is not totally wrong, because basically the mean will give you the center of gravity of your object, the mean coordinates, and then the first-order coefficients will basically give you, where is it? The first-order coefficients will give you basically the elongation along x and y, the variance along x and y, the second-order coefficients. Yes? The zero order is basically the number of points. The first order is the mean, and the second order is the variance. And you can use more. They are difficult to understand, but they can be useful for describing your object. But I think the Fourier descriptors code better your shape. But still, you might want one day to see that somewhere at least. And I will not describe how you can make them invariant. Frankly, this is not very much used, but you can even make them invariant to a lot of things, but I will skip that. This shows how invariant they can be for an object that is translated, rotated, and scaled. And you can see in some references the values that show indeed. Okay, very last, I think it is the very last part of the course. And I stop after. Axis of inertia. This is the last part I wanted to see. You remember what, you see intuitively what is an axis of inertia. Do we have mechanical engineers in the room? Yay! Can you remind me what is an axis of inertia? Mathematically or intuitively?
So mathematically, it's the integral of r squared times an infinitesimal mass.
Something like that, yeah? And intuitively?
So I see it as the mass of rotation.
Yeah, the axis around which it rotates with minimum moments. So if you have a distribution of mass, you find the axis that goes best through this mass, equilibrating the mass. If I have a binary object, obviously it will be the axis crossing my object like that and another one like that. Okay? And the mathematical definition is given here, and this corresponds to this intuitive definition. The axis of inertia is the axis that minimizes the variance of the shape projected on the axis. This is what she said. The axis that basically equilibrates around it the distribution of the points. So, an axis from which the projection of the points on this axis has minimum variance. All the others will less nicely fit my object. So basically what I have to calculate is what is the variance of a shape with respect to a given axis. This is basically the projection, the inner product of my axis and each point of my object, centered. I calculate that, and I will have to find what is the U that minimizes this projection. Yeah?
Something like independent component analysis, or?
Not independent, but principal.
The principal should give maximum variance?
No, actually, it gives you the axis for which you have the maximum variance along the axis, or the minimum across.
Across.
But this is principal. This is exactly principal component analysis. So basically, you calculate that, and this is really the projection of each point on an axis across. And if you develop that, so what is U is basically in 2 dimensions. Let's say in 2D. Yeah? This is the 2D vector describing my axis. It can be 2 dimensions. And these are the x and y coordinates of each point of my object and the center of my object. And so by doing the cross product and doing that for all the points of the object, I get a measure of how well this projection, what is the value of this projection. And now if I develop this term here, like that, there is a square here, so I develop it. I realize that at the end, I can basically get U out of it. And so it's U, a matrix U. Do I have it in the next slide? Yes. It's basically, by developing the central term, this term here, it's U times something which, in terms of coordinates, it's x and y times x and y for all the points of my object, 1 to n, 1 to n. You see, it's the sum for all the points of xy, xy times xy, xy. So xy, xy times xy, xy for all the points. Yes? So this is 2 times n times 2. So at the end, it gives me a 2 by 2 matrix, which is the matrix where I have those values here, 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 and here. 2 by 2 because I'm considering an object, a 2D object, the picture of that, not the 3D, the picture of that. So for the 2D object, the covariance, I said the term, this matrix is 2 by 2. And it has, on the diagonal, obviously, the variance, horizontal and vertical variance of the object. So we are back to the moments, by the way, but fewer. And these are called the covariance, x, y. And this matrix is called the covariance matrix of the object. If I have a large 2D object with millions of points describing my object, its covariance matrix has dimension millions of points of a 2D object. What is the size of the covariance matrix? Millions by millions? 2 by 2? It's 2 by 2. It's 2 by 2. It's the sum of millions of points that give me only estimation of the variance of the objects along x and y. The covariance matrix of an object is the 2 by 2 because the object is 2D. If you have a 3D object, it will be 3 by 3, even if you have millions of points. So the covariance summarizes the distribution of the shape of the 2D object, independently of how many points you have in your object. Yes? Okay. This is the covariance. Now, how do I calculate the U that minimizes this expression? This is a typical eigenvector problem. And so the axes that go through the object the best way are those that minimizes this projection. This is typically the eigenvectors of T. So to calculate the main axis of a shape, you just calculate its covariance matrix. If it's a 2D object, you get a 2D, 2 by 2 matrix, and you calculate 2 eigenvectors of that matrix. You get 2 vectors. The one corresponding to the highest eigenvalue is the main axis, and the eigenvalue gives you an information about the length of that object along its first main axis. The second eigenvector gives you the second axis. The second eigenvalue gives you the width of the object. And you can even calculate the angle of the object from the values of the eigenmatrix as well, from the values of the covariance matrix as well. So now, if you want to calculate if an object is elongated, and I go back to a previous slide that I skipped, elongation is basically defined by the eigenvalues of the matrix of inertia for the mechanical engineers, covariance matrix for the others. The covariance matrix of an object is the matrix of inertia. I have a binary object, so it would correspond to a physical object with equal material everywhere, with equal weight. If I have a physical object which is more heavy on one side with material more dense, then it would be a bit different. But here, the correspondence to what you have learned in mechanics is really like I have a binary object, so I calculate the matrix of inertia of an object which would be an homogeneous object.
Can you actually use weighted systems to improve your categorization?
Weighted in terms of?
If you say, like, I don't know, for example, red parts are more important than green parts.
Interesting. So this is really a mechanical engineer point of view. You would have some parts that are heavier than others. Yeah. That's what you have in mind. So you want to favor, to describe the axis by favoring the axis to pass to some color. Try and tell me. I have no idea. I've never seen that, but why not? Here it's really like an object is binary. And so, now you know how to calculate the axis of inertia, the main axis of an object, which is useful also for comparing objects. Because instead of doing the long gradient descent that we discussed before, which can be long, because we want to register the two rectangles that you mentioned before, just calculate the axis of the two rectangles and just say, now I want to align the axis. And this is not iterative anymore. You calculate the axis, you align the axis and the center, and you're done with your comparison. You just have to calculate the remaining distance. This refers to what I have seen in the previous hour. Yeah?
Yeah, but then it's an eigenvalues problem, which is iterative problem.
Well, the eigenvalue of a 2x2 matrix, I think I can calculate it analytically. I think.
If we use also an axis in grayscale.
Yes? Then we are back to what she said. If you use the grayscale value, you will calculate the axis considering that the grayscale corresponds to the weight of your object. So this corresponds to the principal component analysis of a non-binary random variable. It's more like a random variable which is continuous or at least non-binary. And that's absolutely correct. The definition will just say the x here will not be 0 or 1, but it will be the value. And the center of gravity will not just be the mean geometrical center, but weighted by the values. But it's very much the same. Huh? And so now we have a lot of things, right? We can describe an object by its contour, by its skeleton, by its it's not capacity, it's compacity, obviously. Moments, axes, wow, I was tired at the end. Axis of inertia, and so on. And so next week, you will have to do that. You will have to do something very similar to that. And we will do it this year on a database, which is a typical database used for deep learning, MNIST, which has millions of characters. And I will only ask you to do that on 10 of them. But the goal is really also to get you familiar with the MNIST database and this deep learning stuff that you might see in other courses. Questions, comments? Was it clear? I say yes, at least. Okay, so I expect your report for the first lab by the beginning of the next one. By means before. Before the beginning. Generally, I received a lot of them during the night. I think some of you thought that it would be for today because I received a lot of reports tonight, this night. So you still have another week, if you don't know it. But upload it on Moodle before the beginning of the next lab, which will start next week at 8:15. Feel free to start before. If you start before, you don't have to upload your report before you start, right? There was a request for some people wanting to start before. Do it so that you come at the session with good questions. There will be the data set, the description. There will be a Jupyter notebook again. Sure.
Is it possible to have maybe a small
tutorial
office hour before Friday? Because for the previous lab, we didn't have actually any opportunity to discuss about.
Before. You want to discuss it before? Because you were not available at the time of the...
No, about the previous lab, because for the previous lab, we didn't actually add.
The first lab.
Ah, so you still want to have some office hours for the previous day. Yes, that's a good idea. Well, that's a good idea. That's a possibility. So, yes, why not? I will manage. I will manage to have an office hour, yeah, an hour or two where the assistants would be available for you before next Friday.
Yeah, a lot of questions.
Ah, that's a good idea. That's a good idea, actually. That's a good idea, yeah. I will manage to do that today or on Monday. More questions? I hope it was not too long with only one break. It's okay? You survived? So I wish you a very good week. And I'll see you in, I think it's in 2 weeks, where we'll have a very nice, well, I hope what you will appreciate is a very nice lecture on classification. This is my favorite one, so I hope you will like it as well. Okay? Have a good week. See you soon.